All right, so hello everyone again. So this is the second talk of today's quasi-world seminar. Our second speaker is Ziqiang Li, and he is going to talk about ergodic optimization and visual metrics. So please, Ziqiang.
Thanks, Misha. So thanks for the opportunity to give a talk here in the quasi-world. And today I'm going to talk about some new development in ergodic optimization, especially in connection with visual metrics and our quasi-world. And this is joint works with my colleague Jian Ding and my collaborator Yiwei Zhang. All right, so let me just give the basic definition in the most general setting. We consider a compact metric space and a continuous map on the space, and a real valued function continuous called potential phi. And we consider, since F is the dynamical system, we can consider F invariant Borel probability measures on the space, the usual setting in ergodic theory. And then we can ask, which measure, we can define a measure mu is called phi maximizing if the integral of phi against this measure is equal to the sup of the same integral over all invariant measures. And then we denote, the sup by beta phi, which is some kind of energy we will discuss in a second. And then the set of phi maximizing measures is, for convenience, denoted by M max of phi for this talk. All right, and the study of this kind of phi maximizing measures, this field is called ergodic optimization. It has many connections with other fields of mathematics. Well, first of all, quasi-world, and for example, visual metrics. And it has some deep connection to physics and Lagrangian dynamics, in particular, Witt-Km theory, and thermodynamic formalism, and random graph. For example, maximizing maximal mean cycle problem in random graph theory. And it has connection to max plus algebra or tropical algebra. All right, so let me just use one quick slide. I'm not by no means an expert in this area. This first connection between ergodic optimization and the Witt-Km theory, but there is a very deep dictionary between the so-called weak Kolmogorov Arnold-Moser theory and our ergodic optimization. And this dictionary is listed here for a few important notions in these two fields. So for whoever is interested in maybe one of the fields, this is a good dictionary to consider, and there is some reference available. So that's all I want to say in this talk about this dictionary. But this is a very influential dictionary developed by the group of Mani, most notably Contreras. All right. Now, for me, the more motivating connection is through thermodynamic formalism because, well, I worked a lot in this direction. So what is the connection? Well, in thermodynamic formalism, if we can recall a few definitions, we consider the so-called measure theoretic pressure, which is defined to be the sum of the measure theoretic entropy plus the integral of phi. And then the important measure called equilibrium state is just the measure mu phi, which maximizes the measure theoretic pressure. And then more classically, we consider measure theoretic entropy, and the measure that maximizes the measure theoretic entropy called measure of maximal entropy. Now, then we can ask, what else do we want to maximize? We maximize the sum and we maximize this term. So of course, we can maximize the remaining term. And this is the focus of our talk, the phi maximizing measure that maximizes the integral. Okay. And it also has connection to thermal formalism through zero temperature behavior and ground states. So a ground state is a weak star limit of the equilibrium states as the so-called inverse temperature tends to infinity. So here we can consider a parameter family of potentials T phi, T times phi, where this T is called the inverse temperature. So when inverse temperature T converge to infinity, we basically have the temperature converge to zero. So what does happen when the temperature converges to zero? Well, things freeze, and it has a very interesting interpretation in this theory, as we'll see in a second. Now, but for now, we can. It's easy to see that if the topological entropy is less than infinity, then each ground state is a phi maximizing measure. So the ground state is the zero temperature limit. Ground state is linked to ergodic optimization to phi maximizing measure by this statement. But in general, though, ground states are non-unique. So there is a series of work of Raymond, Sherratz, Hockman, and Coronel, and my collaborator Riva Letelier. And so in that case, by this result, we know that phi maximizing measure is not in general expected to be unique. However, well, we always are interested in questions of uniqueness and existence and uniqueness for any object we define in mathematics. Same here. So for existence, things are much simpler because, well, integral is continuous with respect to the weak star topology on the space of measures. So clearly we know by the weak star compactness of the set of invariant measures, we know the phi maximizing measures always exist. And even though in general phi maximizing measure is not unique, we know that it is generic in very good settings. It is known to be generically unique. By the work of Jenkinson and many others, we know that for generic phi in any reasonable space of continuous functions, there is a unique phi maximizing measure. Okay, so by this we can consider ourselves done for now regarding the question of the existence and uniqueness of phi maximizing measures, and then but there is a lot more to be looked at. From physics side. So in physics, there's the so-called principle of least action. So we want to consider for a fixed nice dynamical system and a fixed nice parameter family or space of potential functions, we want to understand the phi maximizing measures for all, if not possible, most functions phi. And along this line, there is a conjecture of Hunt and Ott in 1996, published in a physics journal, asking predicting that for typical chaotic systems and a typical parameter family of smooth functions, the most values of the parameter, the maximizing measure is unique and is supported on a periodic orbit. The important part here is being supported on a periodic orbit. This is what I said earlier. When temperature goes to zero, we expect things to freeze. Well, the measure is supported on a periodic orbit. That's one interpretation of being frozen. And but this conjecture is a little bit more too vague. Well, it's a physics journal, and so we call it meta conjecture. So to make it more precise, there is a conjecture of Yuan and Hunt in 1999 saying that, well, for non-invertible uniform expanding maps or uniformly harmonic diffeomorphisms, for topologically generic Lipschitz continuous or C1 functions phi, the phi maximizing measure is unique and supported on a periodic orbit. Okay, so this is a well-known conjecture and has been kept open for quite a while until 2015. There is a breakthrough by Contreras, following a long line of works by many people in the field. And the breaking through result, by contrast, says that for uniformly expanding dynamical system and topologically generic Lipschitz functions, there is a unique phi maximizing measure, and then this measure is supported on a periodic orbit. And then the original conjecture of Yuan and Hunt for hyperbolic systems was eventually verified and established by the work of Huang Lian, Ma Xu Zhang in 2019. All right, then we should let's go back to the original paper of Hunt and Ott in 1996, and they asked a few very interesting questions leading to many research in the area. For example, through some numerical experiments. So they ask, are typical maximizing measures of zero entropy? There is many works by starting from Bush, Morris, Jenkinson, Mirandas, and others, and then recently work of Wei Xiaoshen and Rui Gao. Now, and they also asked, does generic potential admit a unique maximizing measure supported on a periodic orbit? So along this line, we mentioned the breakthrough of Contreras and Huang Lian, Ma Xu Zhang. But beyond uniformly expanding and uniformly hyperbolic settings, very little is known, and we will discuss our recent work of my work with Zhang later in the talk. And then the third question, Hunt and Ott asked, does almost every potential admit a unique maximizing measure and supported on a periodic orbit? So here, the key thing is almost every. So this question is asked in terms of probability. Okay, we properly interpreted. And along this line, there's the previous work of Bonk and Zhang. And Bonk discussed about this question in his 2018 ICM talk. And then we improved the work of Bonk and Zhang in our recent work with Ding and Zhang. And then lastly, they asked about the host of dimension of potentials not admitting unique maximizing measure, since we know that in general, phi maximizing measure is not unique or not supported on a periodic orbit. All right, but okay, but the last question is vastly open, and anything interesting, anything about this question would be very interesting. All right, so let me just spend a little amount of time to discuss our work along the line of probability, in the sense my work with Ding and Zhang for the third question mentioned here. Okay, so here we need to first define what do we mean by almost every. So in this setting, so let's just discuss the setting. So we consider the map being one side shift onto symbols, and F being the space of Lipschitz functions with some metric that is fastly decay. And this notion we'll discuss in more details in a second. And then here, the almost every or probabilistic genericity is expressed by the well-known notion of prevalence. Okay, so what does prevalence mean? In order to define that, we need to first define the opposite notion of shyness, just like in the setting of topological generic. There's meager and topological generic. So here, shyness, what does shyness mean? Well, if we consider the space of, for example, Banach space of, for example, Holder continuous functions or Lipschitz functions, but in more general, complete measurable vector space, and then we consider a subset of this space, and a measure mu on the space with compact support. Compact support is very important here. Then this measure mu is said to be transverse to the set S if no matter how we translate this set S by any vector in this vector space, the resulting set is still of zero measure with respect to the measure mu. And then that means the set S is really small. With respect to the measure mu, the set S is really small. So this set S is called shy if there exists such a compactly supported measure mu transverse to S. And then the opposite is prevalent. So a broad subset of the complete metrizable vector space is called prevalent if its complement is shy. Okay, so this is a bit formal. So informally, if we consider a set P, it is prevalent. Then we need to, if we want to say a set P is prevalent, we need to find a compactly supported measure mu, such that for any vector in the space, if we perturb it by adding a mu random term G, the resulting sum falls into the set, even though the original vector may not, with mu probability 1. So any perturbation, any random perturbation almost surely send the original vector into P. So the P is very big. Okay, so we can consider the sum as a random perturbation. All right, so with the notion of prevalence defined, so we can discuss our result. So consider the full shift on binary sequence. This is our dynamical system, and a theta less than quarter, and a sequence AN decaying very fast. Here, in the sense that AN plus 1 divided by AN is big O of theta to the power n. Then for a prevalent subset phi in the space of Lipschitz functions with respect to a metric induced by the sequence A, there is a unique phi maximizing measure, and the measure is supported on a periodic orbit. Okay, so here, how do we define the metric? The metric, roughly speaking, the metric D sub A is defined as the metric with whose diameter, which gives the diameter of cylinder sets of level n exactly AN. The previous work of Bonk and Zhang in 2016 proved the same result under stronger hypothesis. There they assume the quotient is of big O 2 to the power minus 2 to the power n. So here, over there, they have a double exponential, and here we have a single exponential. And then the final target we would like to prove is to even remove the single exponential to make it just zero exponential, or basically just remove n here. Okay, but this is not yet proven. Okay, and in our work, we also prove the same result for the space of so-called little Lipschitz functions, the little Lipschitz space of functions with respect to the same metric. Here, recall the notion in the definition of Lipschitz functions, we have big O. We replace the big O by little small o. We get little Lipschitz functions. And then this is a very important space, very important function space in a field of functional analysis called Lipschitz algebra. And it is, such functions are also studied in the previous works of Contreras in ergodic optimization. All right, so how do we prove such a result? So let me just give a very broad overview of the idea used here in terms of a dictionary. So here we use the dictionary between graph theory and a dynamical system. In dynamic system, the key objects of interest are periodic orbits. These are the periodic orbits can be considered as prime numbers in dynamical system. So the corresponding objects in graph theory, one can consider cycles. For example, on a directed graph, we can have cycles in the graph, and these cycles can be considered as prime numbers in graph theory, and therefore correspond to periodic orbits in dynamical systems. So we want to link our question to a well-established direction in random graph theory called random maximizing mean cycle problem in random graph theory. So here, what does this random maximizing mean cycle problem consider over there? Well, if we consider a sequence of graphs, and on each graph we consider random weights on the edges, and then for each cycle in the graph we can add up the random weights, and then take the average, so divided by the number of edges in the cycle, and then this gives the mean weight, the average weight of the cycle, and then you can ask what's the heaviest, which cycle gives you the heaviest average weight in each given graph, and then almost surely there is only one cycle, and you can consider in this sequence of graphs what the limiting behavior, asymptotic behavior of maximizing the heaviest cycles in each graph. So that is the area of random maximizing mean cycle problem in random graph. And here, if you think a little bit more, you can realize that our question of asking about the maximizing measure, the measure that gives you the maximal integral, is very much related to the maximal mean cycle problem. And my collaborator Jian Ding is an expert in this direction in random graph theory. However, for us to connect our question to the probability, we need to use a class of very special and much more complicated sequence of graphs called diverging good digraphs induced from the symbolic dynamics. Since my focus today is the visual metric, so let me skip the definition of diverging good digraphs, but instead just show you the pictures. So this is number 1, number 2, 3, 4, and very quickly the graph becomes very complicated. So this is usually more complicated than the usual graphs people consider in random graph theory. So it adds more technical difficulty to our investigation. All right, so this is the broad idea of our work with Ding and Zhang along the line of meta conjecture of Hunt and Ott in the probability sense. Now let's move on to the quasi world, and here we study complex dynamics. And for the audience, I think most people know the basic notion of complex dynamics, which studies iteration of rational maps. So let me skip this, even though we still can enjoy some nice pictures of Julia sets. All right, now from the ergodic theory point of view, the simplest rational maps to study are the hyperbolic rational maps. One characterization gives us that a rational map is hyperbolic if for some open neighborhood U of the Julia set, the map restricted to U is forward expansive. And in particular, a hyperbolic rational map has no critical point in this open set U. A critical point is a point at which the derivative of the map is 0. All right, so we want to consider the Yuan-Hunt conjecture beyond uniformly expanding dynamical systems, and this is a very open direction. And so in particular, we want to consider this question in complex dynamics. And then in complex dynamics, the source of non-uniform expansion, the troublemaker, comes from the critical points in the Julia set. So we consider a relatively simple non-trivial case, a rational map that is a rational map is post-critically finite if each critical point is pre-periodic. So such rational maps are also called rational Thurston maps. And more generally, we can consider non-uniformly. So we can consider Thurston maps which are postgrid finite non-homeomorphic branch covering maps on the topological two-sphere. And in the works of Bonk and Meyer and Haïssinsky and Pilgrim, we consider a special class of Thurston maps called expanding Thurston maps. So a Thurston map is expanding if there exists a metric D that induce the standard topology, and there exists the Jordan curve containing the post-critical points, which is defined to be the union of forward orbits of critical points, such that if you consider the kinetic component of the complement of inverse image of the Jordan curve under n iteration of the map, then the kinetic component has diameter uniformly converge to 0 as n goes to infinity. Okay? So you look backward and the map is shrinking, so you call the map expanding in the forward sense. And this definition in particular is independent of the choice of the metric and the curve. All right, so once we recall the notion of expanding Thurston map, then we can state our result for the rational case first. So let F be a rational expanding Thurston map. So in other words, a postgrid finite rational map without periodic critical points. And sigma be the spherical metric on the Riemann sphere. Then for sufficiently small beta, and for open and dense subset of phi in the space of little beta holder continuous function. So, or in other words, little Lipschitz function with respect to the snowflake of the spherical metric by beta, by the exponent beta. Then in this subset, in this open dense subset, for each phi, the phi maximizing measure is unique, and it is supported on a periodic orbit. Okay, for lattice map, we can prove a cleaner result, more complete result. So same setting for lattice map, and sigma be the spherical metric, and alpha beta between 0 and 1, alpha beta not equal to 1. Then for open dense subset of phi in the little beta holder continuous function, or open dense subset of phi in the usual beta, usual alpha holder continuous function, the phi maximizing measure is unique and supported on a periodic orbit. We actually prove the result using visual metric in the most general setting. Let F be an expanding Thurston map and D a visual metric, and the same alpha and beta. Then for open dense subset of phi in the little beta holder continuous function, or open dense subset of phi in the usual alpha holder continuous function, the same result holds. The phi maximizing measure is unique and supported on a periodic orbit. So these are, in some sense, the first results of typical periodic optimization conjecture or Yuan-Hunt conjecture in non-uniformly expanding setting. Okay, so so what are the difficulties? So in non-uniform expanding dynamical systems, usually we lose control of the regularity of dynamical quantities. For example, in the classical study of thermodynamic formalism, when we consider the Roux operator, which is well defined by this, but basically the point is it's an important operator, and then this operator, unfortunately, in the non-uniform expanding setting, does not send alpha holder continuous function to alpha holder continuous function, and then you cannot use the spectral property of the Roux operator, which is very important in the usual theory in dynamical system. Similar issue also happens in ergodic optimization. Here we, instead of Roux operator, we consider the Bush-Lax operator, or Bush operator, or some people call Lax operator, which is defined by sending each continuous function u to the max of u plus phi, evaluated at the preimage point of of X. Okay, and if you look at these two operators closely, you can realize that the Bush operator can be considered as the max plus version of the rule operator, or the tropical version of the rule operator. And with this observation is very important in our latest investigation. All right. So now let's discuss the general strategy in the study of in our study of post-critic finite rational map or expanding system map for similar ergodic similar questions in ergodic theory, including thermodynamic formalism or ergodic optimization. So we want to use perspective from geometric group theory and the cost geometry, basically use the visual metric to convert difficulty from non-uniform expansion to some relatively independent difficulties. For example, we want to uniformly distribute the difficulty in dealing with the cost geometry of the otherwise uniformly expanding visual metrics, dynamics with respect to the visual metrics, especially if we look backward, look along the iteration of the map. And then here, the cost geometry really is in the sense of spatial, also temporal. So sometimes we have to iterate enough times of the dynamic system to get the controls we want. And then even though we look at the visual metrics, sometimes we still have to face with very concentrated difficulties in terms of the combinatorial structures that defines the visual metric. But because the difficulties can be concentrated, we can try to focus on them and overcome the combinatorial difficulties if possible. All right, and then depending on the questions we investigate, from time to time, we need to convert between the different metrics and then use the relation, the cost geometric relation between the various metrics for our investigation. But at least with respect to the visual metric now, we get our operator, be it the rule operator or the Bush operator, it does preserve the alpha holder continuous functions. And then we can consider the operator theory. Okay. Now, so let me just recall for some people in the audience, what are the visual metrics in the dynamical setting for our expanding system maps. Let F be an expanding system map and C be a Jordan curve containing the post-critical points. And we still consider the connected components of the complement of the inverse image of the C under n iteration of the map. And call these connected components, or rather the closure of these connected components, the n tiles. Then the visual metric can be characterized, even though it's built from geometric group theory via Sullivan's dictionary. In this setting, it can be beautifully characterized by the following two properties. D is a visual metric with expanding factor lambda if it satisfies the two properties below. The diameter of any n tile is comparable to lambda to the power minus n, and the distance of two disjoint n tiles is bounded from below by a quantity comparable to lambda to the power minus n. Okay. All right. So the name visual metric, as I mentioned, comes from geometric group theory, and there is a much bigger connection behind from Sullivan's dictionary. So Sullivan's dictionary connects the geometric group theory to complex dynamics. In particular, in the Sullivan dictionary, we have on the left, we have co-compact Kleinian groups. On the right, we have rational expanding system maps. And for Gromov hyperbolic groups with boundary S2, it corresponds to the topological maps called expanding system maps we defined earlier. And over there, the famous conjecture of Cannon corresponds to various characterization theorems of rational maps, asking what are the topological maps that can be realized by the rational ones. Okay, so one form of Cannon's conjecture due to Bonk and Kleiner says that the boundary at infinity of Gromov-Haber group is homeomorphic to S2 if and only if the visual metric is quasi-symmetrically equivalent to the spherical metric. The related result in dynamics is due to Bonk and Meyer and Haïssinsky and Pilgrim. It says an expanding Thurston map is conjugate to a rational map if and only if the visual metric is quasi-symmetrically equivalent to the spherical metric. Okay, so I think for this audience, let me not define quasi-symmetry, or it's the quasi-world. Okay, so now let me discuss in a little bit more details the strategy for the proof of our result in ergodic optimization for expanding Thurston maps. Okay, so there are three key ingredients. So first of all, we want to establish a so-called Manias lemma. So for each potential phi that is alpha Holder continuous, we want to construct H that is also alpha Holder continuous, which is very important to not lose the regularity. And this H satisfies the property that phi plus H composed with F minus H. This is called coboundary induced by H. This basically normalization of phi on the left is always less than or equal to the energy, the maximum integral, the maximum value of the integral. Okay, so in this step, we need to use the Bush operator in our proof, and the Bush operator act on alpha Holder continuous function to still get alpha Holder continuous function is important in this step. And then we want to establish very fine closing lemmas for our dynamical system. Now, our dynamical system is non-uniform expanding. It has a very bad places, basically the critical points and the post-critical points. And and then the closing lemmas, if you vaguely remember, has very strict forms, quantitative forms that is related to the expanding behavior of the dynamic system. But in our case, our dynamic system is not uniform expanding. It gives us trouble. So we want to instead, as I mentioned, this is kind of a combinatorial issue. So we want to avoid the post-critical points and the critical points whenever we need to formulate local versions of the closing lemmas we want to establish. And then we want to combine 1 and 2 to get to perturb our phi, because we want to eventually prove the property of a generic phi. So basically, for each phi, we want to perturb it. And then when we perturb it, because of the non-uniform expansion, we want to do a local argument away from post-critical points sometime and critical points some other time. And we also want to, depend on the question, the result we want to prove. For example, for rational Thurston maps, or for lattice maps, we want to convert between back and forth between visual metric, spherical metric, and a canonical orbifold metric in the right time in the analysis when we do the quantitative perturbation in the last statement. And if we do it in the right time, we can get our result. Okay, so I think because the second and the third component of our proof is quite quantitative and a little bit technical, so I don't want to spend too much time explaining this part of the difficulty in this talk, but you can always find the details in our paper, which is on arXiv. But instead, I want to focus more in the remaining of the talk on the Manias lemma. Okay, so we want to prove that let F be either expanding Thurston map or equipped with the visual metric, or post-critical finite rational map without periodic critical point, equipped with the caudal or spherical metric. We want, and then we consider Holder continuous phi. We want to prove the existence of Holder continuous U, satisfying that phi minus the coboundary induced by U is always less than or equal to the maximum energy, beta. Now, here we want to also emphasize that the statement is purposely formulated less quantitative than it should be, because we are considering two cases. So in the case of visual metrics, we want to actually preserve the Holder exponent. So U should be alpha Holder continuous if phi is alpha Holder continuous. Okay. All right. So so how do we prove such a result? How do we prove such a result? Through the proof, you will see it's the connection between ergodic optimization, the closer connection between ergodic optimization and the thermodynamic formalism. So okay, let's recall the setting. We in a very general setting, we consider compact metric space and a finite to one surjective continuous map, and the Bush operator sent a function, a real value function to a real value function given by the formula we mentioned before. And we can normalize, sorry, so this is per se. We can normalize per se by per se minus beta. So this, if you are familiar with thermodynamic formalism, you can see the close connection or from how we do things in thermodynamic formalism. We also over there we also normalize the potential in a similar fashion, and everything can be translated from the language of max plus algebra. All right. Now let's keep the formula on the top to remind us, and then we want to observe that this Bush operator is actually has very many good properties. So this in the same setting, you can the Bush operator is in property 1 and property 3. It's actually max plus linear. You can, so in max plus algebra, you replace oops. You replace the real number with addition and multiplication by real number union minus infinity, and the operation becomes max and plus. Should probably change a different color. Okay. So property 1 and 3 can be considered as max plus linearity of the operator, and the operator also iterate nicely under the normalization, and moreover, it behaves nicely with respect to taking limit, pointwise limit. Okay, so this is a nice operator, and now we observe a little further that if we replace the potential by a normalization of the potential by a coboundary induced by a continuous real value function U, then the resulting, and we can even add a constant to it. The resulting set of resulting potential have the same set of maximizing measures as the original potential. Okay, so we are free to normalize the potential. Similar thing is true in thermodynamic formalism. All right, now we consider the Bush operator with respect to the normalized potential, and if we can find eigenfunction, the max plus eigenfunction, or in other words, the fixed point of the Bush operator with respect to the normalized Roux operator, then the further normalization, so the further normalization of the potential denoted by phi tilde has a very nice property. So what property does it have? Okay, so first, its energy is exactly 0. So the maximum integral is 0. And actually, the potential is pointwise less than or equal to 0. So where the potential is 0 is than of interest to us because we want to maximize the integral. Okay, so we consider precisely this set. Okay, so we consider the inverse image of 0 under this new potential, and we consider the points in the space whose forward orbit always fall into this set. This set is denoted by K. Okay, and this set K is very interesting because the set of maximizing measures satisfy each maximizing measure, the support should always be in K. All right, then once we observe this, then we just want to remark that in the end, we normalize the potential and we construct this K, and we want to investigate close the property of this set K in the final proof of our main result. And therefore, it is key to find the eigenfunction of the Bush operator, the max plus eigenfunction of the Bush operator. All right. So and then how do we do this? We do it through a quantitative study of the Bush operator. And in order to do a quantitative study of Bush operator, we need to have good quantitative bound. And through the visual metric, it's possible. So, for example, the forward image of the alpha Holder continuous function U under the Bush operator and iteration of the Bush operator has a uniform upper bound in terms of the Holder constant of phi and the Holder constant of U. Okay, so this is a key distortion lemma for the Bush operator, and if you're familiar with Summerline formalism, you realize that exact same thing is true for the rule operator. Even the notation is the same. Well, the notation is for Bush operator, we use L for historical reason because some people also call it lax operator. All right. Now, so how do we then in the end construct this max plus eigenfunction of the Bush operator once we do have the quantitative bounds? Well, the construction is done by this proposition. So this is the last proposition that gives us the construction of the eigenfunction of the Bush operator, and this proposition as well as its proof is translated precisely verbatim, almost verbatim from the statement and the proof of the existence of eigenfunction of the rule operator by replacing the real numbers by the max plus algebra. Okay, so but if you are not familiar with Summerline formalism, this is precisely how we do it. We define the function u phi to be the limit sup of forward iteration of the function 0 under the Bush operator with respect to the first time normalized potential, and this function satisfy well. It is uniformly bounded with a good quantitative bound, and it is even alpha Holder continuous if phi is alpha Holder continuous, and with good quantitative bound, and it is indeed the eigenfunction of the Bush operator. Okay, so I think that's kind of in some sense a sketch or strategy for our proof of the Manier lemma for expanding Thurston map. And this idea of our work in expanding Thurston map can be quite useful in other settings in ergodic optimization. For example, we can also study the maximizing measures, study the typical periodic optimization conjecture, the Yuan-Hunt conjecture we mentioned in this talk for the famous Gauss map, which takes the inverse and minus the integer part. Or we can also study the so-called beta transformations, which is given by this formula. These are the work in progress, collaborated with my student Ying Huang and my undergraduate student Zelai Hao and collaborator Oliver Jenkinson. And here the philosophy is, well, what are the critical points? What are the bad points for Gauss map and for beta transformations, for beta numbers? And what are the post-critical points for the Gauss map and the beta transformations? And you can investigate, you can kind of build a dictionary between these different maps, and you can use local argument for the closing lemma and for the final perturbation argument, thinking that, or mimicking the proof in the case of expanding system maps. But of course, there is a difficulty for each different setting, which is not the theme of this talk. Okay. Thank you.
All right, thank you, Ziqiang, for the great talk. Yeah. So, any questions?
Yeah, thank you, Ziqiang. Very, very interesting talk. I have a bunch of questions, so maybe I'll just start. So you considered like a snowflaking of the map and all your sort of estimates and all this, a snowflaking of the visual metric, right? So
yes.
Is that just because the visual metric is only unique up to snowflaking, or do you need to snowflake to have expansion large enough, or why do you need to snowflake in all your sort of estimates? I just wanted to, I don't know, get a little more insight.
Yeah, actually, that's a very good question. So there is a few point of views. So first of all, indeed, let me go to the result for expanding system maps, which we don't need to snowflake.
Okay.
So here.
But
so
here you like d beta is a snowflaking, right?
So for the usual space, usual alpha Holder continuous functions, for the usual alpha Holder continuous functions with alpha can be 1. Okay, but in the little alpha Holder continuous function, I think, well, we leave this formulation for the cleanest, not for the most general setting, because actually for expanding, because well we don't expect our reader of the paper or of the talk to be as expert as you for expanding system maps. So they will probably not ask. But for expanding system map, except the lattice maps, this beta can also be made into 1 by just choosing a bigger okay. Expanding factor.
So, sorry, can you just remind me here actually what was small lip again?
Yes. Okay, so it's
maybe you had it somewhere, but maybe I forgot.
Yes. Yeah, it's here. Yeah, I did it a little bit too fast.
Okay.
So here, the usual Lipschitz functions are defined by big O.
I see. Yeah.
So in some sense, I think these functions are of interest by historical reason, because in the works of Contreras, he already considered such functions in ergodic optimization. But also on the other hand, I think somehow, if you look at the literature, there is a huge literature on some other area of mathematics where people focus on this space.
Another question.
Yeah.
Okay. I don't know. Maybe some other people want to ask questions first, but I don't know. I have more questions, but
let me at this point stop the recording, maybe.